Okay, right, number 2 in my sort of sequence on splitting and spin-spin coupling. What I want to do now is show some common splitting patterns. They're a bit out of context, but they will help you quite a lot just to focus on some common sort of patterns that you may or may not get in a sequence in a molecule, okay? But again, it's to be taken as an overall sort of thing, okay? But you will see these will help you to focus on certain things later. So what I'm going to do 6 of these. So I'm going to draw 3. 1, 2, 3. Like that. I hope you can see them all. Squash them at the bottom. Yeah, it's all right. Okay, right. So let's have a look. A sequence in a molecule. You often get a sequence like that. CH2, CH2, a lump of hydrocarbon. Okay, so what you're going to get for splitting like that. Now, those look equivalent to me, but I don't want them to be equivalent. I want to have the peak for that and the peak for that separate, okay? So it doesn't really matter. I just need to sort of alter their chemical shifts so they're not equivalent. So, you know, I'm going to put, this is purely arbitrary, so I'll tell you what, I'll put a Cl bang on there and a Br on there, and I know for a fact that they're going to have slightly different chemical shifts. Okay, now I'm not interested in the scales, I'm not interested in the actual chemical shifts, I'm not even interested in the integration particularly, I'm just interested in the splitting patterns. Right, so two protons on that carbon, fine, right? Are they going to be split? Yes, they are, because that carbon has an adjacent carbon with 2 protons on it. N is 2. So that one, call that number 1. Call that number 2, right? That one, the peak from those 2 there, is going to be split by the protons on the adjacent one with 2 on it. N is 2. Those protons are going to be split by those protons into 3, n plus 1. So, in other words, line along the bottom, baseline. Let's do these ones first. Adjacent 2, n is 2, plus 1 makes 3. Those 2 split into 3. Triplet. Number 1. These 2 here, same deal. Those 2 there, joined to a carbon. Right, yeah, fine. Is there an adjacent carbon? Yes, there is. Does that adjacent carbon have protons on it? Yes, it does. 2. So N is 2. So those 2 here are going to be split by those adjacent protons. The peak here is going to be split by those 2, n plus 1 into 3. In other words, 2 triplets, classic splitting pattern, doesn't matter which way, 1, 2, 2, 1, doesn't matter which one. An integration peak laid on the top, so there's no correlation, will tell you that there's 2 and 2 in that environment. You get a sequence like that, you're bang on, you've got a CH2 and a CH2 in your molecule, no doubt about it. Right, let's have a look at another interesting one. How about we have this? You get this quite a lot, well, sometimes, it's a giveaway. I'm sort of knocking it up into this sort of A level now. There, okay. What are they joined to? Who cares? But let's say we're isolating them by joining them to some kind of, I should have put that in red really because I'm not that interested. So we'll have OC. Let's say they're joined onto some kind of ester. They're an ester type thing. Right, all I care about is what peaks are going to be produced by those protons. Well, there's a number of things to consider. 3 protons on there, joined to a carbon. Does that carbon have any protons directly attached to it? No, it doesn't. N is 0. So n plus 1 is 1. So these 3 protons are not going to be split into anything. So there's 3 there. Okay, same with those 3 there. Joined to a carbon, which is joined to a carbon with nothing on it. 1 peak. Okay, singlet as it's called. Those 3 there, joined to a carbon, joined to another carbon with nothing on it. In other words, those 3 protons are A, all equivalent, B, unsplit. Okay, so you should be able to deduce this yourself, all right, without waiting for me. And I'm not interested in looking at the chemical shifts. Like I said, I'm avoiding the scale. But you're going to get a one line in a singlet. These are triplet, triplet, singlet. And the giveaway, singlet, it means they're isolated. 9 isolated protons in that because they're all equivalent. Okay, job done. Now we're going to do, and again, these are a bit tricky to look at straight away, taken a bit out of context, but you often get benzene rings, aromatic rings in NMR spectroscopy. They've got to be joined to summit. So you can have a monosubstituted one where you've got, it's fairly obviously one of the hydrogens has been substituted for a carbon. So there's other things attached to that benzene ring. It's monosubstituted. But there are, never mind what's on here, we'll deal with these later. We're just looking at the benzene ring now. There are 5 hidden protons there. And although I wasn't going to talk about chemical shifts, if you've got an aromatic ring, you're always looking for something in the region of about 6 to 8. Okay? If you look at this, 6 to 8, yeah, 6 to 8. That sort of thing going on. Banged on. Okay, there. Right, now, what do you look for? So you look for a region 6 to 8, and then you look for, these interfere. These split with each other in a sort of a characteristic way. So, let's have a baseline. What you're looking for in the region 6 to 8 are aromatic. Is it monosubstituted? Is it disubstituted? Well, you're looking for a little cluster of splitting which you can't sometimes even count, and sometimes in the exam it might even look a bit like this, like fine splitting, and they won't tell you how many it's been split into or anything like that. So how do you know? Well, you know it's aromatic because it's in the 6 to 8 region, but probably when that's integrated, which is information they do give you, 5 protons in that environment. That tells you you've got a monosubstituted benzene ring somewhere in your molecule. Simple as. Multiple splitting. Okay, so not a singlet, not a doublet, not a triplet, not a quartet, not a quintet. A cluster, often called a multiplet. But they do tell you what's going on. But that is a key signal, actually, a key clue, right, which we'll come back to later. Okay, I've got 3 more for you on this particular video, which will be good. Hopefully, so get rid of that, get rid of that, get rid of that, and then we'll get rid of this. Yeah, there you go. 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 Alright, so that's cool. Right, another common sequence might be this. CH3, again possibly joined in some kind of ester. H, right, you should be able to deduce that, no problem. Okay, let's see whether we can do it a bit fancy. Chemical shift, HCO. Right, so these here, again, I'm not going to bother with the chemical shifts, I'm not interested, so we'll just do a baseline and then let's see whether you can see. But I always forget the baseline, and baseline there, and a baseline there, and a baseline there. Alright, so let's see. Proton-wise, environment-wise, 1 equivalent, 2, so 1, 2. Right, again, I'm not interested where they are in the chemical shifts. Okay, I keep saying that. Right, just in the splitting patterns. Now, I want you to have a go at this. I want you to produce splitting patterns for this for me, please. Okay, right, so... Right. H joined to C, joined to an O, H joined to a C, okay, right. Let's do number 1. 1, 1, equivalent. 3 in that environment, 3 in that environment. Okay, do they have an adjacent carbon? Yes, they do. Does that have an adjacent carbon? Yes, it does. Does that adjacent carbon have any H's on it, any protons? Those won't split those. Because if you look, those 3 are joined to that carbon. Adjacent is that one in the middle. That's beyond adjacent. Okay, so it's only the adjacent one you need to worry about. You don't have to go further down the line than that. So, yeah, 1, so 3 joined to a carbon with 1 on it. And those 3 joined to a carbon with 1 on it. Shouldn't be a genius to work out, therefore, that they're going to be split. N is 1, N plus 1 is 2. So you're going to get, and like I say, the order of these might be wrong, otherwise I'll be here all day. You're going to get a doublet, okay? This one here, okay, HC, is it joined to a carbon with protons on? Yeah, 3. And down here, carbon with protons on, 3. So N is 6 for this proton here. So in other words, N plus 1, the peak, giving that proton there, N plus 1, 7. So you're going to get a beautiful thing that looks like this. Probably looks a bit like this in the actual spectrum. Okay, then you put the integration on. So there you go, split into a doublet, integration. 6 in that environment, all 6 split into, N is 1, so into a doublet 2. Okay, this is going to be 7 peaks because that one there, 1 split in the 6 adjacent, N plus 1 split into 7. Okay, so, and actually you could call it a septet. Right, like that. Okay, so doublet, septet. Okay, so notice there's no correlation between the amount of splitting and how many are in the environment. So that's split into 2, but there's 6. That's split into 7, but there's only 1. No correlation at all. And also, if they're adjacent, they split each other. End of. So that's a possibility, right? Again, when these are contextualised, they'll be easier for you. Okay, I should have probably done this one first because it fits in with the monosubstituted benzene ring. How about you get something like this? What do you expect to see? Because of course I'm always going backwards. You take that and you deduce that, and you take this and you deduce that. So right, so this one again, aromatic, and it's a di-substituted aromatic ring. So you're expecting things to appear in the 6 to 8 region. Telling you it's aromatic. What do you expect to see in that? Well, a multi, because these protons here, there they are, they're invisible. They're all going to interfere with each other. They certainly are. They're all going to split each other. So you're not going to get one peak of 4. That one peak of 4 is going to be split into a little, again, sort of a little cluster. Okay? I don't want to get into, so you look for a little cluster here. Never mind how many are in it, it's hard to say. Little cluster, right? But either way, integrating in, if that cluster is in the region 6 to 8 and integrates to 4, you've got a di-substituted benzene ring. Simple as. Okay? And now to finish on this sequence, CH3. Like I say, if you're not quite sure about this, let me look at some examples. It'll come back to you what I'm saying now. It's hard without a context, so I appreciate that. So here, let's identify this. Call that number 1. Call that number 2. Okay. Let's put some chemical shifts on this for this one, shall we? 0, 10, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, because I'm going to have to use all that after. Right, again, you should be able to do this. I'm not doing a table because the table really is later when we go the other way. We'll do tables soon enough. Right, let's have a look at number 1, HCO. Chemical shift wise, HCO is 9 to 10. So there's going to be something here. That proton is going to appear here, okay? And it's joined to a carbon, okay? Does that carbon have an adjacent carbon? Yes, it does. Okay, does it have protons on it? Yes, it does. How many? N is 3. So in other words, N plus 1 is 4. So the peak from that proton is going to be split by those protons into a quartet. Okay, in the region 9 to 10. Look at this one, so that's number 1. Look at this one, number 2. C double bond O. Let's have a look at the little table of data. C double bond O, HCC double bond O. 2 to 3. 1, 2 to 3 down here. Okay, so yeah, those 3 there, they're going to give you a signal. Integration 3, they're joined to a carbon, it's got 1 on it. So in other words, those 3 there are going to be split by that proton there into N plus 1 into 2, a doublet. So in the region 2 to 3, there. Okay, 2. You put an integration peak on it. One proton in that environment, 3 protons in that environment. That illustrates a number of things about NMR. I mean, these are quite far apart in terms of chemical shift. So that one's, 9 up here, 9 to 10. That one's 2 to 3. It's irrelevant, right? It doesn't matter how far apart they are in the spectrum, right? It's how far apart they are in the molecule. And if they're adjacent carbons, they will be split. Chemical shift is not about, it's irrelevant, okay? They will split each other because they're adjacent in the molecule. And the other thing is, don't ever confuse the amount of splitting with the integration, because that's split into 4, a quartet. That one there split into 4, but it's only 1 proton in that environment. That is only split into 2, but there are 3 in that environment. So again, it's counterintuitive, but you get there if you do a few of these. Okay, that's a few things in your armoury for later. Cheers, guys. Thank you.